The previous slide and look at writing nuclide symbols for these two different uranium compounds. So we have uranium-235, it's an isotope of uranium. So if we were to write a symbol, we would have a uranium. 235 is the mass number. That goes here. Whoops. Excuse me. And then the atomic number, we can put it here for sake of show, 92 for uranium. And like I said, different isotopes are going to have a different number of neutrons, a different mass number. The protons, the atomic number stay the same. So an isotope of uranium that is uranium-238 is going to have, it'll look like this. Okay. So that's all review. That's something that you should remember how to do. I know that it always takes a couple times writing it out again after it's been however many months or years since you've done this. But this is something you're going to be needing to do for this chapter. Writing these types of symbols. You take your symbol for your element, put the mass number superscript to the left, and the atomic number subscript to the left. We don't often write the atomic number subscripted because it is synonymous with the atomic symbol. So if you know the symbol, you know the atomic number. If you know the atomic number, you know the symbol. So if we go back, that looks like this. All right, mass number, top left. All right. So the first thing we're going to look at are different types of decay and writing nuclear equations involving those different types of decay. There's a number of different ones that we're going to look at, and we're going to look at how these different radionuclides, things that are radioactive, emit particles or radiation. So basically we're going to see a number of unstable nuclides and how they decay. The rules for balancing nuclear equations are very straightforward. This is going to feel very easy compared to some of the things we've been doing recently. So the rules are that the mass numbers on either side of the arrow must be equal, and the sum of the atomic numbers on either side of the arrow must be equal. Okay? So we're going to write out our nuclides with the mass number and the atomic number, and summing all of those mass numbers got to equal on the same side, different sides of the arrow, same with the atomic numbers. We are going to also see a number of different particles that we're going to use in our nuclear reactions, and they're going to have specific symbols that we're going to use for them. So neutrons are going to have a mass number of 1 and 0 atomic number, right? No protons, right? It's just a neutron. The proton is going to be represented by the H for hydrogen. So it has 1 proton, and so atomic number 1, mass number 1. The electron then, we give the symbol E, and then a -1 where we would put the atomic number, and that will come into play. We will add a -1 to certain things. And that's basically standing in for the charge. Alpha particles, you may have seen these before, get represented by helium. Let me zoom in a little for you. With a mass number of 4, an atomic number of 2. And then we have beta particles, which are essentially electrons. And I will be using this term in some of the nuclear equations we're going to write here later on. And then a positron is basically an electron, but it has a positive charge instead of a negative charge. It has the same mass as an electron, just has a different charge, opposite charge. So you will need to be familiar with these, know these. Okay. So let's start, so we have different types of radiation as well. So those were our particles. Now we have different types of radiation. Alpha radiation is basically just alpha particles being emitted. So it's still our alpha nuclei, or helium nuclei. Beta is a type of radiation, it's our electrons. And then gamma radiation, this is a little bit different. So this is actually a photon, it's a high energy photon. And we'll talk about how that arises. Different masses shown here, things like that. But you need to be familiar with these different symbols. Okay. So let's look at alpha emission. So alpha emission, we're going to have a nucleus that's going to decay and give a new nucleus and an alpha particle. Something that's going to be radioactive, usually the heavier nuclides. Okay, we'll talk about that too. So the decay of uranium-238, is an alpha emission. So I'm going to write out my reactant, which is our uranium-238. And we know that it's alpha emission, so I'm going to write out one product, helium, our alpha particle. And you should be able to predict what the other nuclide is that will result. And that's based on adding and subtracting the appropriate mass numbers and atomic numbers. So for instance, we now have an atomic number total of 2 on the product side. So our nuclide that forms needs to have an atomic number of 90. And which element is that? Thorium, right? And that means we're going to need a mass number of 234. So you'll see that 4 plus 234 gives us 238. 2 plus 90 gives us 92. And so that's about as difficult as it's going to be for writing these types of decays. Okay? I recommend figuring out your atomic number, relating that to a symbol in this process. Okay? These are one and the same, 90 and thorium. Let me go back. Another example for alpha decay is that of radium. So radium-226 has an atomic number of 88. It decays by alpha emission. So we'll form our alpha particle. And what's the other product? I'll give you a couple seconds here to write out that other product. All right, so you should end up with the element with the atomic number 86, which is radon, and we'll have a mass number of 222. So everyone see how that comes about? All right. So I've got a video for us about radium. I think this should play through the speaker. Let's give this a whirl.
In the 1920s, a factory in Ottawa, Illinois, some 90 miles southwest of Chicago, hired young women to make watches and clocks glow in the dark. How? They painted a substance containing a small amount of radioactive material on the timepieces. The women exposed to the material, radium, eventually developed deadly and sometimes horrifying side effects. But the names of these young women, many of them teenagers, are often missing from the history books. So, author Kate Moore tells her stories in her new book, The Radium Girls, the dark story of America's shining women. And Kate Moore joins us now. Kate, welcome to Chicago, and welcome to Chicago.
That's really behind.
First of all, give us some background on radium itself, because once upon a time, it was everywhere. How come?
It certainly was. It was seen at the time the girls were dial painting as a wonder element. People thought it was an elixir of youth and a cure-all, and actually the mayor of Chicago used to drink radium water as a health tonic. The recommended dose was 5 to 7 glasses a day.
Oh my gosh. And so how did the rise of World War I impact radium and its use?
It had a huge impact. So the girls were not just dial painting watches and clocks, they were also doing their bit for their country. So they painted aeronautical dials, the luminous instruments that one needs on aeroplanes and trucks and ships. So of course, when America joined the First World War, the radium industry exploded and they suddenly needed hundreds of girls to fulfill this demand.
And there were factories in New Jersey and in Ottawa, Illinois. Why was it mainly women who were hired at these factories?
Well, I think part of it is the nature of the work. If you think of a tiny dial such as a watch, the numbers that they're painting were sometimes as small as a single millimetre. And so it was very delicate handiwork. Records actually show that some of the dial painters were as young as 11, most were teenagers. And I think their small, nimble hands made them particularly skilled for this delicate handiwork.
And they use a particular technique called lip pointing. What is that?
It's incredibly dangerous, as we know now. And what the women would do was to slip their paintbrushes between their lips to make a fine point. And that was the only way they knew of to get the brush thin enough. So on almost every number, they would slip the brush between their lips.
And in doing so, they would ingest radium.
That's absolutely right. And of course, you know, the girls did ask, does this stuff hurt you? I found first-person accounts for the women when I was researching my book that said the first thing we asked was, is it dangerous? But they were assured, because of the belief in radium as this wonder element, that in fact radium would put roses in their cheeks. That's what their managers said.
And yet the managers knew better, because there had already been research about the dangers of radium. In fact, you write that the men in the factory took precautions. They wore lead vests, and what else did they do to minimize?
Yeah, they kind of wielded ivory-tipped tongs when they were handling the radium. They weren't allowed to touch it with their bare hands, and they had to take enforced vacations because it was too dangerous to be so regularly in contact with radium. Now, the women were using a small amount, and that was seen as the difference. So from the very turn of the century, only a few months after the Curies had discovered radium, they knew that a large amount could kill a man. And yet the radium firms who were making money out of radium conducted their own research, and they determined that a small amount of radium was beneficial. And that's why there was this industry that sprung up with radium cosmetics and radium toothpaste and chocolate and all those other things. But it was the radium firms that were funding and carrying out that research. Because
independent research showed that even small amounts were very risky. And there were some side effects. Some of them were horrifying, upsetting to look at. We had some images. More sensitive viewers might be
Oh yeah, get ready.
might be upset by this. More on the side effects that people, mainly women, suffer.
Well, radium poisoning takes a while to show itself. It's very insidious. It can take 5 years or more. And what the women realised was happening, it would start very innocently, an aching limb or a loose tooth. And they would go to the dentist, and the dentist would extract that tooth, not knowing what was happening to the women. But then the next tooth would start to hurt, and then the next tooth, and the next tooth, until the Radium Girls didn't have to go to the dentist anymore because the teeth fell out on their own. And you're showing an image there of Molly Maggia's jawbone. You can see that there are holes in it, yes. And what happened was the radium settled in the women, in their jawbones, in their arms, in their legs or their spines, and it drilled holes in them, just as you've just shown in that image.
At some point, the women connected the dots, and they started suing the companies.
Yes.
What happened as a result of it? What happened during those battles?
Well, I think the important thing to say is that this really was a group effort. The Radium Girls is not just one heroine. It's all the women. It's Catherine Donahue, it's Charlotte Purcell, it's Grace Fryer. And this is a story of women standing together to stand up for their rights. It was incredibly hard for them, not only because they had to overturn the received wisdom of the age because everyone thought that radium was safe, but because they were battling these enormously powerful corporations who were making money hand over fist, so they had the financial resources to eke out this fight as long as it took.
But not only that, you point out that that the people in Ottawa, the town, turned against the women
Yes.
because.
Well, at the time the Illinois women were trying to hold the company to account. We're in the midst of the Great Depression. This is a story that spans American history. And of course, in the midst of the Great Depression, millions of people are out of work, they're starving. The lines in Ottawa to the soup kitchens are extraordinary.
So it was a valued employer, and they didn't want to,
Exactly right,
people didn't want to
yes.
jeopardize it.
And so the women were shunned, people turned their backs on them, the clergy said they shouldn't be doing it, yet these women fought on despite all the odds against them.
How did they eventually win?
They were assisted actually by a Chicago lawyer, Leonard Grossman, who was the most extraordinary man. He was someone who would work for free. His son told me when I interviewed him for the book that he used to accept shoes as payment. So this was a man who, someone, if they were in trouble, no matter how much money was in it, and in fact in this case there was no money, this was a moral fight. And Leonard Grossman assisted the women in Ottawa, and he was the one that led them kind of through this charge in the courtrooms to make sure that justice was finally done.
You present the women very realistically, almost like you get to know them. How did you do that?
Well, it was an enormous research process, and you're right that what I wanted to do in the book was to bring the women back to life as much as I could, because I felt they'd been lost behind this anonymous moniker of the Radium Girls. So to bring them to life, I had the pleasure of interviewing their family members, their sons, their sisters, their daughters, nieces, nephews, and they told me what the women were really like. But perhaps most importantly of all, my research uncovered the women's own words and their own accounts of what had happened to them. And so through court testimonies and letters and diaries, I've been able to bring the words and the voices of these women after 100 years back to life in this book. And the book for me is a platform for the Radium Girls. I'm just their representative sitting here before you now. The Radium Girls book is their story, and it's their voices that you will find shining and speaking out through its pages.
And the legacy continues in the form of changes and reforms. What are those reforms?
Well, it's a two-pronged legacy, really. So there's the protective legislation that their fight for justice engendered. So workers' rights are championed in a way that before the Radium Girls took their case to court was not true. The women thought about legislation changes. Yet they also left us a scientific legacy. We all know here in Chicago of the Argonne National Laboratory, and there the women were studied for decades. They exhumed their bodies, and the living women were tested voluntarily, and they have left a scientific legacy about the effects of internal radiation that scientists have termed is incalculably valuable.
And we're almost out of time, but there's a very eerie point that you make in your book, and that is that radium has a half-life of 1,600 years. So these women's bones are still glowing?
Yes, and their families described to me how in their darkened sick rooms the women would give off a faint light of their own, because this radium that they once used to make dials glow in the dark has now settled in their bones, and the women themselves are still glowing in their graves.
Kate Moore, thank you so much. Fascinating and disturbing story.
Kind of crazy. Has anyone heard this story before about Radium Girls? Any murderinos? Okay. All right. A couple of takeaways from that. So, first, the radioactive decay process is that they're talking about is the alpha decay. But even more importantly than that, one of the takeaways is worker safety. So one of the legacies of Radium Girls, as she mentioned, is to have regulations in the workplace that ensure workers' safety. And this is along the back along the line is the reason why you wear goggles in lab. I mean, so some people had to suffer in order for us to start using our heads about what's safe and what's not. All right, so let's move on. Any questions on that? Yeah.
So L particles can only break
Yeah, I believe that's true. So you have to ingest it in order for it to be a major issue. And I think that's part of the reason why the management in those watch factories didn't have any complications, because they were being very careful to not come in contact with the radium. Which is another reason why I wanted to wear gloves when handling that uranium. So, okay. Anything else before we go on? It's kind of a downer, wasn't it? I think that story is really, I mean, it's just absolutely insane to think about how that whole process. I mentioned Murderino, so if you don't know what that is, there's a podcast called My Favorite Murder that I tend to listen to. They did a story on the Radium Girls, and they did a really nice job on it. So if you listen to that podcast, I recommend that episode. If you don't listen to that podcast, I recommend that podcast. Anyway, beta emission. Okay, so a beta particle is essentially an electron, all right? And so these are high-speed electrons that are emitted by an unstable nucleus. And essentially what happens is a neutron is converted to a proton. And the physics behind this, we're not going to get into, but it does involve subatomic particles like quarks and antineutrinos and things like that, that I honestly don't really understand completely. So something I would have to study a bit more. But this beta emission is really important when we think about carbon dating. So we'll talk a little bit about carbon dating. So this is a method of determining the age of a substance using the carbon-14 isotope. So carbon-14 decays by beta decay. So if we write out our reaction, carbon-14 is going to form our beta emission. So here's our beta emission, it's the electron, okay? And now from this, you can figure out what the remaining product is going to be. Again, summing up mass number and atomic number. So on our product side, in order to sum to 6, we need to have a nuclide with the atomic number of 7, which is nitrogen. And because our mass number is 0 on the product side, it remains the same. So we form nitrogen 14. Okay. Gamma radiation. This is where we give off a gamma photon from an excited nucleus. And basically, what happens is the nucleons, the protons and the neutrons rearrange to form a more stable arrangement and give off a photon in the process. This is used in medical imaging. If anyone's ever had a PET scan or anything like that, basically what you do, you usually ingest unstable or metastable technetium. So it's technetium 99. And we often will abbreviate or use the lowercase m to symbolize it as metastable. This has the atomic number 43. And what happens is metastable technetium decays by gamma emission. So it gives off a gamma particle and forms a more stable technetium. So it's just rearranging those protons and neutrons in the nucleus. But in medical imaging, so you would take some sort of drug or compound that is doped with technetium, and that drug would go to a particular organ of interest. It could go to the skeleton, gallbladder, any number of organs, tumors, that kind of thing. And then it stays in that particular location and will decay. Metastable technetium has a really short half-life. I believe it's a few hours. But essentially then, once you go into an imaging machine, the gamma rays are detected and an image is created. And so it's the gamma rays that are emitted from this technetium that is being used. Kind of an interesting process. All right. positron emission. So I mentioned that a positron was simply an electron with a positive charge. So it has the same mass of an electron. The positron is given the symbol E to represent the electron, but a subscript 1 for the positive one, positive charge. Another isotope of technetium uses positron emission to become decay to become more stable. So technetium 95. Oops, there we go. Atomic number 43 will decay by positron emission. And I'll give you a second there to write out the remaining product. Okay, so we should have a nuclide with the atomic number 42, and that's molybdenum. And again, the mass number remains the same at 95. Questions on writing any of these decay equations, anything like that? Okay. A couple more here. Electron capture. So in electron capture, the nucleus captures an electron from an inner orbital. I think on a previous version of the slides I wrote outer orbital, so make sure if you have those slides just to cross that out and write inner orbital. So in this process, a proton is converted to an electron, or excuse me, converted to a neutron. Okay, we'll give the proton this symbol, superscript 1 for mass number, subscript 1 for atomic number. In the conversion process, basically you have this inner orbital electron interacting with the proton. There's a -1 there to form the neutron. So if you look at those mass numbers and atomic numbers, you'll see that they are equal on both sides of the scale. Electron capture is what potassium 40 is decaying by. So potassium 40, atomic number 19, decays by electron capture to form argon with an atomic number of 18. I was looking up random things that you have around your house that give off radiation, so I could play with the Geiger counter. And I guess Brazil nuts have a large amount of potassium. I didn't have any Brazil nuts at home. But now's the time to buy them because the grocery stores have all those bins of nuts for holidays. So if you want to test some Brazil nuts for radiation, just let me know. Okay. Spontaneous fission. Here we have an unstable nucleus that decays spontaneously and releases energy. And that is the important part. We'll take advantage of that in certain cases. More on that later. So uranium-236 is a great example. Mass number 236, atomic number 92. So this decays and forms yttrium-96, atomic number 39, plus iodine 53, mass number 136, and 4 neutrons. Could you predict the products of this? Probably not, but if you were given 2 of the 3, yes, right? Okay. So if you're thinking about types of questions we could be asking, it's simply going to be doing the math, adding up the atomic numbers, adding up the mass numbers. All right. So there are some ways that we can predict the types of decays that different nuclides will undergo. It's not a perfect system. There's no law that states what's going to happen, but there are some trends, some patterns. Your book calls this the patterns of stability. So some nuclides are stable, carbon-12, carbon-13, and some are unstable, like carbon-14 has a certain half-life that decays, and we can use that to our advantage. One of the things that plays into this is the ratio of neutrons to protons. And so this plot shows the number of protons, the atomic number, can't see that, on the x-axis, and the number of neutrons on the y-axis. The red line shows a 1-to-1 neutron to proton ratio. The blue dots show the stable nuclides, and the yellow dots, those are dots, but it's kind of blurry, but they represent unstable nuclides. And so what we see is that up to, this is my next slide, for smaller nuclei up to an atomic number of 20, the stable nuclei have a neutron to proton ratio of 1-to-1. So if we go up to 20, that includes these guys. Okay. And so, the other thing that this plot is doing is dividing the number of neutrons by the number of protons. Okay, to give you the ratio, so it's 1. Okay, for the less than 20 or less atomic number. For nuclei with atomic number greater than 20, what will happen is the stable nuclei will have a neutron to proton ratio of greater than 1. So you'll see for iodine 127, we have a neutron to proton ratio of 1.4. It's one of these blue dots in here. Iron, a little bit above as well. Iron 56, you can see this neutron to proton ratio. And so we're deviating from this 1-to-1 ratio. And the reason why that is, I don't believe it is exactly clear, but it has to do with the number, with the repulsive forces in the nucleus. So you've got all these protons with positive charges, and they're in close proximity with each other. And the neutrons are trying to balance that out. And what it's thought is that once you get so many protons, so many positive charges, you need more and more neutrons in order to have a stable nucleus. Let me see where. So you also notice there are no blue dots here. So nuclei with the atomic number of 84 and greater are not stable. There are no stable isotopes. They decay typically by alpha emission. And then there's a couple other rules. So let's call this line with the blue dots, we'll call that the belt of stability. Okay, and for any of the nuclei located above that belt, they're most likely going to decay by beta emission, and anything below that belt could decay by positron emission or electron capture. So there's a couple of ways you can predict what's going to happen. You might see some problems like that. Okay, let's do one more here. Okay, where are we? Yeah. Okay, so radioactive decay chains, these are actually kind of cool. So some radioactive nuclei can't just stabilize by doing one nuclear reaction, nuclear transformation, and then that's it. They undergo a series of transformations until they form a stable nuclide. So, where are we? So if we zoom in here on our plot, this looks at uranium, which was it? Uranium-238. And it decays by multiple transformations in order to get to lead-206. And that's its stable nuclide. And there's different arrows here. The blue, They don't look the most blue, but the blue represents decay by alpha emission, so it's emitting an alpha particle, and then the red by beta emission. And the plot is showing the mass number on Y and atomic number on X. And so you can see when we have an an alpha emission, we change both the mass number and the atomic number. And when we have our beta emission, we're essentially losing an electron. The only thing that's going to change is the atomic number. So that's why we see those occur straight across the chart. So we'll look at a few more radioactive decay chains coming up. Any questions on this so far? All right, sorry about waiting my head today. Have a good afternoon.